Hi, I'm Thomas, and recently I was in a position to make some slides about mutual exclusion, which is an interesting concept to know about, so I figured I'd also make this video for YouTube. And so this is a little bit of an introduction to concurrency. What is concurrency? Why would this happen in a computer system or any other kind of process? And I wanted to kind of demonstrate to you that concurrency is something that actually gets you in trouble in the real world. And then I will sketch for you a classic solution to the so-called mutual exclusion problem, namely Peterson's algorithm. And this is kind of one of the basic classical solutions for this problem. Then at the end of the video, I will say a little bit about what the next things would be that you could look at if this is something that interests you. So first of all, what is concurrency? Well, quite literally, from the Latin, it's running together, concurre. So the context in which you may have heard of this already, it would be like multi-threading or distributed computing or something like that. And from an engineering perspective, it will turn out that multi-threading and distributed computing, it will be an enormous headache. You will not do this for fun if you're trying to make a reliable system. So why would you do concurrency if my claim is that it's a massive faff? Well, it is that, but it also has a bunch of advantages. There are good things that it's going to get you. So why would you do concurrencies? If I have multiple computers, that's actually fine. If you have your computer and I have my computer and we have fun on our own, that's fine. That's not really concurrency, even though things are happening at the same time. The real challenge of concurrency is when you share resources. And so when does it happen? For example, if you put multiple computers on a network, well, first question, why would you do that? Well, maybe you want to play games, send each other messages, but also, and this is where these shared resources come up explicitly, is, well, maybe you have, for example, on the hallway or in your home, you have one printer and you want to be able to print on it from multiple machines or from your phone. Depending on how this networking technology works and how this printer works, maybe it would be bad if all of the machines on the network start sending commands to this printer all at the same time. Also, like, how do you even connect to this printer? There is a wire, maybe it's Ethernet, maybe it's Wi-Fi. If everybody starts transmitting at the same time, then it's going to be collisions, it's going to be bad. You need some kind of concurrency control, medium access control, like how are we going to do this together in a way that will work out? So that's explicitly multiple machines, but there are different kinds of concurrency. So for example, if I have multiple programs on a single machine, why would I do that? Well, of course, that's how computers work, right? You have multitasking. The first iPhone didn't really have it. It was annoying. You want to have, even like on your desktop PC, you want to have your mail program in the background and your browser with multiple tabs. And this should all be running at the same time. It's super useful. Maybe you're recording a video in the background while you're projecting slides. So this is kind of how we've decided that computers work, because it's super useful that you can have multiple programs running at the same time. But then what is the kind of resources that you end up sharing? Well, the processor, the main memory, the devices like the file system or the network, or if you have multiple programs that want to play audio at the same time you're listening to your music, but also to a YouTube video. So there's all kinds of concurrency there. Not only that, and this last one wasn't really a thing when I was a student, but it is certainly now. In a lot of computers, there are multiple processors in a single machine. So even before you start talking about multiple computers, even one computer at some level down there is actually multiple processors running at the same time, running together, and they have to share, well, main memory, and now that also includes like the cache hierarchy, which is a super interesting topic, but we don't have time to get into that, and you're still sharing devices, etc. Okay, editing Thomas here. I'm complaining a lot about how hard everything is, but it's even on the screen. I just forgot to talk about it. Why do you put multiple processors in a single machine if this is going to be so much of a problem? And the reason is we're kind of running into physical limitations, or at least engineering limitations nearing physical limits, which means that we don't really know how to make a single processor faster anymore. And so if we want more computational power, what we're going to have to do is, well, make more processors and make them somehow run together. And that's why this entire concurrency thing has become much more important than it was maybe 20 years ago. It's not all doom and gloom. It's tricky, but we're doing it for a reason. We're actually going to get additional performance out of this that we don't know how to get out of a single processor. Okay, back to the video. So I hope I've kind of convinced you that concurrency is useful. This is something that we want. Having said that, now let's see how this gets us into trouble. And for that, I would like to present to you a mystery of missing mutations. I'm going to do this in C++, but it's subtly different, but mostly something like this could happen in different programming languages, because it mostly has to do with how the computer actually works on a hardware level. So let's say we have a global integer called global, and I have this function f, and it just increments this global integer 1,000 times. This is not like a super useful function. You wouldn't really ever write this. But the entire program to demonstrate the problem is going to fit on this slide. So you really kind of see what the actual problem is that's going on here. So I have this function that increments a global 1,000 times. And I set the global to 0 in my main function. And then I call f twice. And then I output the global. Now, there's no concurrency here. And this is a very simple program. And there's absolutely no problem here. We're going to print 2,000. And that's fine. However, now let's add the concurrency. So what we're going to do is we're going to say thread. So in C++, if you have this thread object and you give it a function, then it's going to go off on a different processor, run this function in parallel. Like the program is going to keep going. F isn't finished yet. We're going to keep going on its own. F is going to get run somewhere. Again, it's a little bit of a simplification, but that's how we're going to think about it now. So basically what this code says is go off while the main program is still going, go off on different processors, go run F on this processor and go run F on another processor. And then in the main processor, we're going to wait until both of them are done. They say, okay, we have done these 1,000 increments. So now we look at the global and we see what value does it have. Here we have actual concurrency. What is the shared resource? The shared resource is a global variable. So now it's demo time. We're going to compile this program, run it, and see what happens. Okay, so there's no trickery at all. This is the actual code that we just saw in the slides. And so let's compile it and run it. So now the question is, are we going to get 2,000? Oh, okay. We are. Next time. Okay. Oh, okay. So it worked a couple of times. Like I said, this is tricky. Now, one time we lost a bunch of the increments. We lost even more. Okay, so how could this happen? Why do we sometimes get to 2,000? Well, there's a number of overheads. Like it takes a while for this one processor to get going and for the other to get going. So maybe if the one processor finishes all of its 1,000 increments before the other one gets going. So let's see if we can, instead of 1,000, let's do 10 million. And now we're going to have a more pronounced effect. It's going to go wrong every time. And so, I mean, we're not even close to 20 million, right? We're getting the amount of increments for like one thread plus a little bit. So this is massive. Like, half of them do work. So what happened? What happened is that this global plus plus, this increment of the global variable, is not what is called atomic. So we're not really going to do the formal definition of atomic, but what it kind of means is that it happens in one step. It is unsplittable. This happens in one go. And if we look at the disassembly of this program, what we see is actually this global plus plus on the processor ends up being 3 instructions. It's get global from main memory into EAX. That's a register, a little bit of super fast memory inside the processor. Every processor has its own EAX. So this is this one global in memory, and we put it in our processor. Then inside the processor, add EAX1, we increment it, and then from the processor, we move it back out from our own EAX back into memory in the global. So this is how things get messed up. This global plus plus is actually 3 steps. If we're in the middle here, then some other processor can come around and also do some of these steps. So atomic means this is an indivisible step. It proceeds without anything else happening at the same time. And in a typical model, what you say is that read and write to memory is atomic. However, modifications, as we just saw, generally aren't atomic. So this was read, modify, write back, and somebody else could come in between. The model that we typically take for how a machine, like multiple processors in a computer, are allowed to do their things, how this is allowed to happen concurrently, is that we say that it has to exhibit sequential consistency. And again, we're not doing the formal definition. Look it up. So intuitively what this means is maybe in real life things actually happen at the same, different things happen at the same time. But the result has to be something that could have happened if things happen one at a time. And the steps of one at a time are these atomic things. So it's not, it has to happen as if we called F once and then the other F, but it has to happen, the atomic things within F, I can interleave them in some weird way, but while one of them is doing a write or a read, that's not going to get messed up by something else. If there's a 42 in memory and I'm trying to read a 42 and somebody else is trying to write a 43, then I'm not going to read somehow 200 or some nonsense. In the typical model, these are atomic. There are also models where if you read while somebody's writing, it's allowed to be messed up, but we're not going to talk about that in this video. So we're saying read and write is atomic, and we have this sequential consistency thing. Let's quickly demonstrate how our missing mutations can come about, which is, okay, we have this shared global memory, 42, and then processor 1 goes, reads to 42, increments it, but this is inside EAX, this is inside processor 1. So now processor 2 goes, reads to 42, because in memory it's still 42. Now processor 1 writes to 43, back to memory, but processor 2 doesn't know, it still has the 42. It's going to add it, it's going to get 43, and it's going to write back to 43. So they both think they've done an increment, but the global has only incremented once. As a little bit of a challenge for you, in this model, what is the, if I have these two processors doing 1,000 increments each, what is the, well, clearly the highest number that you could get in global is 2,000, but think about it, what is the lowest number you could have at the end of the program? Think about it. Okay, so that was intuitively kind of what's going on here, but let's introduce some terminology. So these three instructions here, you could call them a so-called critical section. And the idea of a critical section is it's a piece of code that only one process should be doing at a time. If one of the processors is in here, the other shouldn't also start doing this. Then the question is, what should it do? Probably it should wait. But that's another can of worms. A critical section is a thing where we say only one process should be doing this at once. And now we get to the title of the video, Mutual Exclusion. Mutual Exclusion is the property that only one processor can be in this piece of code at a time. It's the property, but it could be, you could have a mutual exclusion algorithm or mutual exclusion protocol, which is an algorithm or protocol that guarantees that only one processor is in here at the time. Now, these two terms come from a paper called Solution of a Problem in Concurrent Programming Control by Dijkstra. Yes, this is the Dijkstra from the shortest path algorithm. This is 1965, Technological University Eindhoven, and it's a really short paper. It's only one page. Here's the entire paper. There's 4 sections: introduction, the problem, the solution, the proof. There is no conclusion, there are no references. The last sentence of the paper is, and this, the author believes, completes the proof. Fair enough. And I'm not a historian, but I think this is the paper where critical section and mutual exclusion first show up. And in this paper, Dijkstra argues, well, this is actually a problem in real life. You share devices, and can we actually make this work? And his answer is yes, we can make it work. We're not really going to talk about his algorithm. It's a little bit more complicated than it turns out it needs to be. And we're going to specifically look at a two-party mutex algorithm. But real quick, let's do this intuitively, right? So critical sections exist in real life. So, for example, as a shared resource, you could consider a small doorway that you can't pass through multiple people at the same time. And so how do you solve this problem in real life? How do you end up not bumping into each other? Well, just see whoever gets there first, and they go. And if somebody's in the door going through, then you wait until they're gone. So it's kind of a basic way to intuitively do mutual exclusion on critical sections. But it also shows that maybe this is going to have consequences, because if this is very busy, maybe you need to make a queue. And also, like, maybe if you arrive almost at the same time, like, how do people solve that in real life? Well, one of the ways that you do that, well, people say after you. And then you could go, no, you. And this is actually something that Dijkstra worries about in the paper explicitly. He doesn't want there to be a possibility, even probabilistically, that people, for an infinite amount of time, end up saying, no, you, no, you, no, you, no, you to each other. So what we kind of want for a mutual exclusion protocol is that it, first of all, that it guarantees mutual exclusion, but also that it is in some way fair, and that it deterministically terminates in finite time. Let's do one more example where this isn't entirely true, even though in practice, in the real world, it does work out, because there are humans involved, and they're not literally bound by this algorithm. So if you have a four-way road intersection, right? So you have a road and a crossing. So there's four directions that you can come from. And so what's the protocol there? Everybody knows you yield to traffic from the right. But can you see a problem here? I would say yes. If from all directions a car comes almost simultaneously and it's not obvious who gets to go first, then you're kind of stuck there and nobody can move. This is called a deadlock, when nobody can move anymore. Everybody's waiting for somebody else, but there's kind of a cycle in there. So how do you solve this? Well, in practice, on the road, well, one person is more assertive than everybody else and just starts going. Or you get into this after you situations where you start looking at each other. And this is actually also how you could solve this in programming. Like, you could make some of your processes more assertive. Like, okay, if we're stuck, then I go. But I'm getting ahead of myself. Let's look at the general setup of how we think about mutual exclusion algorithms and the concept of busy waiting. Up here, I have the shared memory, which at the moment we don't have yet, and then there are two processes, process 1 and 2, and what I want is for these processes to basically be mirrored. They're going to run the same code, except one of them knows their processor 1, and one of them knows their processor 2. The kind of way that we're going to look at this code is we're going to say there's basically just one critical section, and I don't really care about the code outside of the critical section, because whatever concurrency is allowed to happen there is fine with that. But we have this particular part, this critical section, where we say, okay, if processor 1 is in there, then process 2 shouldn't, and the other way around. Basically, the way that we're going to analyze these programs is we're going to imagine that they're infinite loops, both of them, and there's normal code at the start, normal code at the end, but at some point there's this critical section, and then we're going to make an entering protocol and a leaving protocol, which are small, hopefully small, pieces of code before we go into the critical section and after we come out of the critical section, that together these processes are now going to never be in the critical section at the same time. And because there is always this forever loop in the normal code, I'm going to leave that out. And I don't care what the critical section itself is, I'm interested in these protocols. So I'm only going to show you the entering protocol and the leaving protocol. So it should probably share some memory, right, to communicate between the processes. And for mutual exclusion, you typically take some bits, you call them flag, where each process has a flag, and basically the intuition is going to be like, watch out, I'm in the critical section. Or maybe it's, watch out, I'm going to go into the critical section, but we'll see. So let's try to make this work. We have flag 1, flag 2, and process 1 says flag 1 to true, and process 2 says flag 2 to true. So, no, this doesn't do anything. Nobody looks at anybody else's flag, and everybody's just going to go into the critical section. So this is not a mutual exclusion protocol. Let's try to make one. So here the idea is, well, if the other guy is in the critical section, then I shouldn't go. So what we're going to do is we're just going to make a while loop. We keep looking, we keep reading the other guy's flag, and or process 1, right? So if flag 2 is true, then the other guy is in the critical section or almost going in. So we shouldn't go in. We should wait here. And so this thing here is called a busy wait, because we're actually doing something. We're doing this loop, but the only thing we're doing is waiting. We're waiting for flag 2 to be false at some point. And we're working in the model here where we say that reads and writes of flag 1 and flag 2 are atomic. This is not ever going to be screwed up. You're not ever going to see anything other than true and false, and it's just in this interleaved model. Like, we don't know who gets to go when, but either I read it before the other guy writes it, or I read it after, but these are the only two options, and nothing is screwed up in the middle. So is this a good mutual exclusion protocol? Think about it for a second. I'm going to say, not quite, but it does achieve mutual exclusion. Process 1 and process 2 cannot both be in the critical section at the same time. But do you see a problem with this? Think about it for a second. And I'm going to say, no, there's a problem here. And it's a deadlock problem, like in the four-way intersection. You can end up infinitely waiting for each other. So what we can do is process 1 goes, set its flag to true, process 2 goes, sets its flag to true. And now we're both infinitely waiting on each other, and nothing can ever happen again, and we're screwed. Well, maybe this is unlikely in a sense of timing, because like this has to happen quite specifically in order to lock ourselves out. And this is actually one of the tricky things about concurrency bugs and problems with concurrency, because if you use this code a lot of the time, it'll probably work. Depending on how long your critical section is and how often you're trying to go in there. But as we saw with the missing increments, like depending on exactly how the real world setup is, sometimes things don't go wrong and it's fine. And then every once in a while your program just hangs, and this is a problem. So of course we always want to prove things, but concurrent programs are especially difficult to debug empirically. So it's very important to prove these kinds of things. This is not a good mutual exclusion protocol. And the problem seems to be we set our flag and then we wait, and we can end up waiting for each other. So what happens if we flip it around? Like, so first we wait as long as the other guy is in there, and then as soon as the other guy isn't in there anymore, we quickly set our flag to true and go into the critical section. Does this work? Is this a good solution? It can't really deadlock, but I mean, this is worse, right? I mean, this one doesn't guarantee mutual exclusion. They can both, maybe both of the flags are false. They both look at each other's flags. Oh, it's false. We can go set their own flag to true and then go into the critical section. So this is a bogus solution. The previous one could deadlock, so it's also not a solution. But this is definitely not a solution. This doesn't even guarantee mutual exclusion. So now let's look at the solution. This is 16 years after the Dijkstra paper. It's Peterson's algorithm, and there had been different solutions in the years in between where maybe you generalize it to more processors or different kind of models, and at some point Peterson comes along. Like, all these algorithms are more complicated than they need to be. Here is a fairly simple algorithm, and he also does it for multiple processors, but to keep it even more simple, we're just going to do it with these two processors, and we're going to do it with only one more bit. I'm going to have a turn variable, and this is going to allow us to do some kind of after you go situation to solve our deadlock problem. And it is at this point important to emphasize that there's only 3 bits: flag 1, flag 2, and turn, but reading and writing them needs to be atomic. So if you actually implement this on a modern machine, don't put these 3 bits in the same integer, because then setting and reading them might not be atomic. We need reads and writes to these 3 bits to be atomic. Okay, so let's do Peterson's algorithm, and you're going to recognize most of it. First of all, you set your flag to true. Like, watch out, I'm going to go in. I'm trying to go into the critical section. Then we set this turn variable to the other process. So on process 1, we're going to say turn equals 2, and process 2 is going to say turn equals 1. So this is kind of our move of saying after you. Like, if we both want, you should go. This is not in the critical section yet. We're still in the protocol. So we don't know in what order this is going to happen. Maybe the other guy is going to overwrite my turn assignment or the other way around. But it kind of doesn't matter, right? If we're both trying to get in and we both try to say after you, then it's kind of a good thing that only one of them succeeds. Like, randomly or for whatever reason, one of these writes succeeds or overwrites the other, and then whoever wins saying after you then waits for the guy and the other guy can go. So we set this turn variable, and then we have this loop, and loop is a little bit more complicated now. While the other guy is trying to go, or is in there already, and it's their turn, then we keep spinning our wheels until one of these things is no longer true. So maybe they're already in there, and then at some point they're finished, I set their flag to false, and then I can go in. Or maybe we're still fighting this after you fight, and maybe it turns out that they set turn equal to 1, and then I can go. So this is Peterson's algorithm. And I'm going to tell you this works. I mean, we would have to go into the model more specifically. We would have to do careful definitions of exactly how this atomicity works, how this interleaving works, what is atomic, and how the scheduling of the different processes works. But in the typical models, this actually works, and I'm going to sketch it for you. But because we haven't done the definitions, I can't really prove it to you. So I've put the code in the bottom right, and first of all, I'm going to argue that we achieve mutual exclusion with Peterson's algorithm. And in order to do that, I'm going to make some observations of what must be true if process 1 is in the critical section, and what must be true if process 2 is in the critical section. They set their own flag to true. They don't share this variable for writing, so whatever they do to it actually works. And it clearly, this flag is true whenever we're in the critical section. Now, what else is true? We cannot go into the critical section if the other guy's flag is true and it is their turn. So if I'm in my critical section, then either their flag was false or it was my turn, and the other way around. So if the other guy's flag is false, then they're definitely not in the critical section and I'm alone. That's one option. If let's say both of the flags are true, then we look at the turn variable, and in order to go in, it has to be, well, your turn, but it cannot be both of our turns. And this is kind of, you have to be a little bit tricky. There's a temporal aspect here, like in what order do we check these things and how does this happen? But this is like the sketch of why this is correct. You have to be a little bit careful there, and I'll give you a little bit of an exercise there, which is our while loop is now complex. It used to be we just read this single bit and we look at it, but now our while loop says flag 2 and turn equals 2, but this is now not really atomic anymore because we have to read flag 2 to our own processor, and we have to read turn, and we have to do this and then we do a decision based on that. But in the meantime, stuff could have happened. So it works. It's actually fine. But this is something that you do actually need a well-defined model for, and then to do a real proof that this is actually how it works. In the original paper, by the way, it doesn't say while flag and turn equals 2. It says until flag 2 equals false, or turn equals 1. It's like the contrapositive, but until loops aren't really a thing. It confused me a second when I was reading the paper, so I've translated to a while loop for you. So this is the mutual exclusion part, and I think that makes sense. And then there's a couple of more properties that you can prove that I will only hand wave here. I've not even defined them. But what you can prove for Peterson's algorithm is that it is deadlock-free, that it is starvation-free, and that there is no lockout. And the thing that we worry about here is, could it be that you end up waiting forever? Could it be that one of them gets stuck and then the other one keeps going all the time, and that's fine. So we don't have deadlock in the sense that nothing is happening, but like one of the processes is getting screwed over and never gets to go. And Peterson's has the property that this is not true. And this is the reason why we say after you. This is the reason why we say no, you go, and we don't say, oh, I'll go. Like this code in the bottom right, we could have said flag 1 equals true, turn equals 1. We could have said, oh, I want to go in and I'm going to go. But that's not Peterson's algorithm. Peterson's algorithm is, oh, I'm going to go, but you can go first. This is the working algorithm that actually has this no lockout property. So in order to prove this, and again, this is only a sketch, for a contradiction, assume that process 1 is in the while loop, this while loop down here, forever. Could this actually be true? So let's consider after some finite time, what could be the things that are currently going on. After some finite time, it could be that P2, the other process, is not trying to enter. Well, then its flag is false, and then we don't stay in the while loop. We can go. Okay. It could be that P2 is also trying to go in, so flag 2 is true, and it is also in its while loop. It's also waiting. So this is the bad part. This is the deadlock. We're both waiting. Turn is either 1 or 2, so somebody gets to go. So we're actually not in a deadlock. So this is good. Now the other part that we were worried about, could it be that P2 gets to go infinitely many times while we always wait? And so could it be that P2 repeatedly goes through the critical section? And the answer is no, because before it actually goes in, before it starts waiting, it says turn equal 1. So the first time maybe you fight about who gets to go. But if process 2 goes the second time, then it definitely sets that we're allowed to go. So again, this is just a sketch, but this is kind of how that works. So that's what I wanted to say for Peterson's algorithm, and I'll finish up with a couple of kind of things that you could look at next. So one thing that you could think about is, can we get the hardware to help us? So here you see a piece of disassembly where apparently we're allowed to say lock, and then we add directly in memory. So here we don't have the read, modify, write problem. We tell the processor, look, over there in main memory, go actually just add 1 to this atomically so that it doesn't get screwed up. But this is kind of kicking the can down the road, because like, how does the processor do this with respect to other processors? So somehow there is some kind of mutual exclusion going on anyway. But since concurrency has become so much more important in modern processors, maybe if you get the hardware to do this, this is going to be more efficient than if you try to do it yourself in software on top of hardware. The memory controller is probably involved, so maybe we can get support from the hardware. Another thing that you could look at is the operating system, because it's kind of the system that manages processes, manages threads, and there's a thing called the scheduler. And nowadays you schedule on multiple processors, but it used to be you had only one processor, and then the scheduler is who decides, okay, now you get to go a bit, now you get to go a bit. And so in the operating system, we have this piece of code that decides who gets to go when. If you have this kind of mutex situation where I want to synchronize these processes in this way to achieve mutual exclusion, and so if the operating system is so involved in deciding who gets to go when, maybe we should involve the operating system in this mutex business, where rather than doing this busy wait, where I'm just spinning my wheels, hammering the RAM, trying to read what happened to this variable, maybe I can tell the operating system, look, I'm waiting for processor to just give the processor to somebody else for now, and maybe put me back in once I can go into the critical section, which now means that the operating system needs to know about what critical sections are and who's waiting for what. And this is a bunch of engineering effort, but this is actually what you do in practice. Like, maybe inside the operating system there's some kind of busy waiting going on, but you probably shouldn't be doing it yourself. Check out what your language runtime and or your operating system can do for you there. Now, as point 1, I said maybe the hardware can help us. Unfortunately, the hardware can also screw us over. So there's a thing called out of order execution, and the idea is this. Let's say I only have one processor, and so the machine instructions come in, and CPUs are massively complex by now. And for a long time, the main business of making CPUs was making single-threaded code go faster. So we get in a position where the CPU goes like, well, okay, I'm already kind of working on multiple instructions at the same time, and I look ahead a little bit, and, I can already start doing that one before this one finishes, and it's fine, because the CPU, of course, also works on a kind of as-if rule. Like here for concurrency, we talked about sequential consistency. The result should be something that could have happened if things happened one at a time. The CPU also works on this as-if rule, like, okay, I don't really have to do the instructions in the order you give them to me as long as the result is the same. Okay, this helps us get better performance. Good idea. But this is dangerous, right? Because now if you think of Peterson's algorithm, what are we doing? We set our own flag, and then we have a busy wait on the other flag. But that doesn't influence each other. So if I think there are no other processors, then I might also first check the while loop, see, oh, I can go, and then at some point I set my own flag. But now Peterson's algorithm doesn't work anymore. So this is bad. Either your processor needs an as-if execution model that takes this into account, maybe actually sees what's going on with different processors, or we now need to tell the processor about things like this, where you have things called a memory fence or a memory barrier, where you could say like, okay, now all of the things that I've read and written up until now need to happen before you do anything afterwards. So you may need to tell your processor about the kinds of as-if reordering that it's not allowed to do. Depending on your processor and your compiler and your language and everything, just writing out Peterson's algorithm may not actually result in code that implements Peterson's algorithm, which is one more reason to use libraries and the operating system to do your mutex protocols for you. Okay, so that was a bit of engineering stuff. So on the algorithmic side, theoretical side, there's also a couple more things that you could do. So we did Peterson's for 2 parties. You can also do Peterson or other kinds of algorithms for n-party mutual exclusion. Like only one of these parties is allowed to be here at the same time, or maybe 3 out of 5 are allowed to be in here. There are general constructions. If you start with a 2-party mutex, then extend this to n. There are algorithms that directly do the n-party mutex. There are lower bounds about the amount of memory that you must share among n parties in order to be able to do mutual exclusion. And then there's the concept of lock-free programming. So in the demo, we noticed that some of our increments went missing, and we saw that the reason for that was that these increments weren't atomic. We had these 3 instructions, and things could go poorly if multiple processors were doing that at the same time. And our solution was to say, okay, this is a critical section. We must guarantee that only one process is doing this at the same time. A different kind of strategy would have been to say, okay, maybe the problem isn't so much that multiple processors are doing this. Maybe the problem is the code, actually. Maybe we can design code that even if multiple processors in arbitrary interleavings are doing this piece of code, it will still work out in the end. And then you get to the idea of lock-free programming. These mutexes are also called locks. In general, this is quite tricky and hard to prove correctness for, but depending on if you can actually get it to work, this is often the high-performance thing to do. As long as your lock-free code isn't massively more complicated than the simple thing with a lock would be, and then it depends on how often would there be conflicts, but again, this was just the introduction. And finally, I didn't show you how to solve the mystery of the missing mutations. Well, the easy solutions, of course, don't use multiple processors, just add 2000 to global and don't make this kind of problems for yourself. But this is, of course, because the demo was way too simple, and that was so that you could really see what happened. We're not going to do it here, but I'll upload another video where I show you in the very simple version how you would solve it, and then I'll make a slightly more interesting example where we will be counting primes on multiple processors, and we'll see the same kind of problem and how you would solve that. I have been Thomas. I hope you had a good time, and see you next time.